Now we're getting into the relationship between electricity and magnetism. And this relationship is going to be what we're dealing with through the end of the class. And in doing these calculations, mathematically, the most difficult thing to deal with is that we have to think of everything now in 3 dimensions. And so we're going to need some new ways of drawing things on a 2-dimensional sheet of paper. So I'm going to start by talking about just some 3D thinking and what's called the right-hand rule. And the right-hand rule is going to be an important tool in this stuff. So the first thing is, we've always so far had the X and Y coordinates in the plane of the page. Now we're going to have a third axis that's going to have to be out of the page. And so this new notation for axes that go out of the page or into the page is going to be like this. If I draw a circle with a dot in it, like that, the idea is that you're looking at the tip of the arrow. That dot in the middle is the point of the arrow coming toward you. So this is a vector coming out of the page. And if I draw a circle with an X in it, the idea of that is that you're looking at the feathers of the arrow of the vector. Think of a vector as an arrow. These are the feathers. So this is a vector going into the page. And I'm always going to be using a coordinate system for this stuff. That has the x-axis going to the right, the y-axis pointing up, and then the z-axis coming out towards us. Okay, so that's always going to be the coordinate system. And one important thing that we're going to do a lot in 3 dimensions is we're going to have to relate a rotation to a vector that's perpendicular to the axis of that rotation. So like if you think of a circle or some kind of rotation that's happening in the plane of the page, then we'd be talking about a vector that's going out of the page or into the page, perpendicular to that. And in defining this relationship, an important tool is going to be the right-hand rule. And so this right-hand rule always does the following thing. It relates a rotation to a perpendicular vector. And the way we're going to see it right now is we're going to have a vector 1 and we're going to have a vector 2 and in order to get from vector 1 to vector 2, you have to have a rotation. So in this case, it would be the rotation would be in that direction. Okay, and then the perpendicular vector is going to be like the output. So I'll call that vector 3, I guess. And that perpendicular vector 3 is what we get out of this right-hand rule. Okay, so where does the right-hand rule thing come into it? I'm going to do a little time-lapse photography here so you don't have to watch me draw. Okay, so this is a right hand, and this is the position of the hand representing vector 1. So vector 1 would be coming out of your fingers like this. Okay, so I'll call that V1. And now I'm going to show your hand position showing V2. If you fold your fingers over like this, V2 is coming out of the tips of your fingers. So this would be your vector V2. Okay. And the order that you're doing this motion matters. So you're always going from V1 to V2. And notice that this rotation to get from V1 to V2 goes like this, the way your fingers curl as you do that. And if your fingers of your right hand do this motion, and you're holding your thumb out like it is here, then your thumb is showing you the direction of that output, that V3. Okay, so V3 is coming out of the page. And so you can always use your right hand to find this relationship between V1 and V2 and the vector that comes out of it. You can do this, in any orientation in 3 dimensions and use this idea. So here's another case, if you have, if your first vector is pointing this direction, okay, and your second vector is pointing out of the page, okay, so in this case, V2 is coming straight out of the page, so I'll draw that as the circle with the dot. That's your V2. Okay. In order to rotate from V1 to V2, your fingers rotate this way. Okay. And so your thumb is pointing in the direction of the output, V3. So that's how the right-hand rule works. And we're going to see that a lot of these vector calculations we do are using the right-hand rule in order to figure out the direction of the output. All right, so before we get into any equations and anything like that, let's get a little practice thinking about the right-hand rule. Okay, so let's say that V1 is a vector into the page, and V2 is a vector this way. What's the output coming from the right-hand rule? And before I do that, let's get used to thinking about the coordinate system. What directions are these vectors in? V1, since our z-axis always comes out of the page, this says that our V1 is in the negative z direction. This V2 is in the positive x direction. And we want to see what the output is. Well, in order to use the right-hand rule and have your fingers curl from V1 to V2, your hand needs to be like this in a thumbs down kind of position. You start with your fingers pointing into the page, and then you curl your fingers back against your hand to put them in V2. In order to do that, your thumb has to be down, and so the output is like that. And so the output of the right-hand rule here is in what ends up being the negative y direction. So one thing, in the examples I drew before, I started with the fingers straight out in the V1 direction and then straight away from the hand in the V2 direction. Here, I guess I drew it a little bit different, where this time the fingers start pointing straight out away from the palm and then end pointing back against the hand. But as long as your fingers can make that motion, as long as that motion from V1 to V2 is in the direction that your fingers naturally bend, your thumb is going to be in that proper V3 direction. Let me do one more example. So this time, let's say that our V1 is straight down and our V2 is straight out. And we want to know what the output is of the right-hand rule for those two vectors. Well, if you put your hand in this position, when your fingers are straight out, they're in the V1 position. When your fingers, I drew them a little bit too balled up, but when they're pointing straight out from the palm towards us, they're in the V2 position. And that means that your thumb is in the V3 position, and so that's the output. Okay. So I would say go through these examples and try to do those motions. Try to make sure that you're making sense out of this. It's funny, when people see this stuff, they think like, oh, like when they see the equations, they think, oh, these equations are complicated. The only thing that's complicated is the three-dimensional thinking and the right-hand rule. Besides that, the equations are super easy to use. So get comfortable with this, and then when we go on to the equations, it'll feel really easy. One thing I want to point out is like hands are useful for a lot of things, grabbing stuff, eating. But really what you would like your right hand, like for this one purpose, I don't really recommend changing your hand out for this, but what you really want on your right hand for the right hand rule is a disc with a counterclockwise rotation drawn on it, you know, a counterclockwise motion on the disc, and a perpendicular arrow pointing out of it. This is what your hand is simulating when you do the right hand rule. So all of this right hand rule stuff would be really easy if you always wore a medallion shaped like this, you know. But this is all your right hand is doing in the right hand rule, is relating a counterclockwise rotation to a perpendicular vector. Okay, now that we've talked about the right hand rule, now we're going to get into magnetic fields. And the meaning of a magnetic field is the same as any other type of field in physics. You know, it's like electric fields, gravitational fields, in physics, all a field means is whatever location you go to, there's a field vector waiting there for you. And it doesn't depend on the motion of the object. It just depends on the object's location at that instant. Okay, so the meaning of a magnetic field is wherever an object goes, there's a magnetic field vector, and we're going to denote these vectors, you know, like with the electric field, we called it capital E vector. We're going to call this capital B vector. And that vector you can think of as sort of waiting in space to be activated by the particle getting there. The SI units for a magnetic field vector our sort of complicated combination of units, newtons over amps times meters. And since that's, sort of cumbersome to deal with, like we have several times before, we give this its own name, the Tesla. And the abbreviation for Tesla is capital T. And we're going to start by thinking about permanent magnets, refrigerator magnets or horseshoe-shaped magnets. Then, later in the next lecture, we're going to go on to talking about how magnetic fields can be created by electricity. That's what electromagnets are. But so for now, we're going to think about permanent magnets. And all permanent magnets have a north and a south pole. One thing that's funny, a little confusing about this, is the north and south poles of magnets were named because they were attracted to the geologic north and south of the Earth. Well, it turns out that the Earth is also a magnet, and like directions of magnets, like poles of magnets, repel each other, like with electrical charges, and opposite poles attract each other, which means that the north pole of a magnet, it's named because it's attracted to the geologic north pole of the Earth, is actually the opposite kind of magnet of the north pole of the Earth. And the south pole of a magnet is attracted to the Earth's south pole, and those are opposite poles. So we're going to talk about magnets with north and south poles. And the north pole of the Earth is actually a south pole magnetically, and the south pole of the Earth is actually a north pole magnetically. Okay, but people have been using this nomenclature long enough that we're not going to change it. Just remember that, the Earth's north pole is really a magnetic south pole. So a fixed bar magnet looks something like this. You have a north on one end and a south on the other end. If you measure the magnetic field vectors coming out of a permanent magnet like this, it would look something like this. They would all be leaving the North Pole. And they would all be ending at the South Pole. Okay, so it would look something like this. And like I said, this is a field, so these vectors have to exist at every point around this magnet. But I would be drawing all day if I filled them all in, but you could fill in some more. And at each one of these, that arrow is telling you the direction of the magnetic field vector. Now, if you have the north pole of one magnet near the south pole of another magnet, these vectors go straight from the north to the south, and in between the two magnets, it's a pretty strong, straight magnetic field vector straight from the north to the south. But then as you get farther away, they start to follow a shape like this. None of them curve, by the way. They're all just arrows. Okay. And one common way to represent these, because these arrows are kind of time consuming to draw, is to represent them using field lines. And the field lines are curves where at every point along the field line, the magnetic field vector at that point is tangent to the field line. So for a fixed magnet like this one, these field lines always start at the north and end at the south. And we put arrows on the ends to indicate the directions. And you can see this is just a little faster way to represent it. And if I do the thing with the north and south of two different magnets facing each other, these field lines look like this. So how would you use these field lines to figure out a specific magnetic field vector? Well, any point you choose, let's choose this point. I just chose that randomly. The magnetic field vector is going to be tangent to that field line in the direction of the field line, so the vector is going to be like that. And if I chose this point, it's going to be tangent to that field line this way. Okay, so all of the information that's conveyed by drawing a million arrows is conveyed with the field lines. And the closer the field lines are together, that means at that location, the bigger the magnitude of those magnetic field vectors are. So since between this north and south pole, the field lines are closest together, going straight across, that's where the magnetic field is the strongest. And that's where the B vectors, the magnetic field vectors, have the biggest magnitude. And what we're going to see is that all of our magnetic related calculations are going to depend on that magnetic field vector B. So that magnetic field vector B is going to be, the main vector that we're using in all these calculations. Okay, so the first calculation, now we're finally to the point where we can do some calculations. And so here's the first fact and calculation. Magnetic field vectors don't have any effect on charged particles at rest. So it doesn't affect charged particles at rest. In order to apply a force to a charged particle at rest, there would need to be an electric field. But this magnetic field vector does apply a force to moving charged particles. And that force obeys this equation. So the magnitude of the force is equal to the absolute value of the charge of the particle. So for this part, we don't care about the whether it's a positive or a negative charge, times the speed of the particle. I'll write that as a capital V. So times the speed, times the magnitude of the magnetic field vector. And the direction, because a force is a vector, it has a magnitude and a direction, follows the right-hand rule. Right-hand rule. Where the first vector is the charge times the velocity vector, okay? And the second vector is the magnetic field vector. And I want you to notice that if Q is negative, then multiplying this by Q has the effect of switching the direction. So if that Q is negative, then this whole vector is opposite of the velocity vector. Okay, so let's do at least one example. Let's see. Yeah, I'm going to do just one example. Let's say that at the exact midpoint, between north and south poles of magnets, of two different magnets, an electron has a velocity of 5.0 times 10 to the 6th meters per second. So very fast. And all the directions are going to be shown in the figure that I draw. And we want to figure out first, what's the force applied to the electron by the magnetic field, so by that magnetic field vector. And then second, given that the mass of an electron is 9.11 times 10 to the minus 31 kilograms, pretty small, what's the acceleration of the electron due to this force? Well, an electron has mass. Before we get into the calculation, an electron has mass, which means that gravity does affect it. But the gravitational force is so tiny because of the small mass compared to the effect of the magnetic field that we're just going to ignore the gravity. Okay, so here is what it looks like. So let's say we have the south pole of a magnet there and the north pole of a magnet here. And this is the exact midpoint. And at that point, this electron is moving in this direction. Okay, so let's go through these calculations. So first we want to calculate the force applied to the electron. Calculating the magnitude of that force is just a matter of plugging the values into the formula. So the magnitude of the force is equal to the absolute value of the charge of the electron, you know. So the absolute value of the charge of an electron, the charge of an electron is negative 1.602 times 10 to the minus 19 coulombs. And now we'll multiply that by the speed of the electron, which is 5 times 10 to the 6th meters per second. And I didn't give you the strength of the magnetic field, but let's pretend that I did. I meant to. So let's say that the, hold on a second. The magnitude of the magnetic field B is 3 times 10 to the minus second Tesla. Okay, so then we have to use the magnitude of that magnetic field, 3 times 10 to the minus second. And what we get for the magnitude of the force is 2.403 times 10 to the minus 14 newtons. And now the harder part, we have to figure out the direction of that force. Well, we're going to use the right-hand rule. The velocity vector, so the first thing that goes into the right-hand rule, here's our velocity vector. Since the charge of, we're dealing with an electron that has a negative charge, so Q times the velocity vector, that negative charge switches the direction. So here is our Q times V. If this had been a proton, then Q times V's direction would be the same as V, because the charge is positive. And now our V2 is the magnetic field vector. Well, we know that the magnetic field vector always goes from north to south pole. So our B vector is like this. And so we want to curl our fingers. So we're going to go, our rotation is going to be from QV in this direction to B in this direction. Okay. And if you think of the right-hand rule, we'd be looking at the hand from the side like this. The thumb is on the other side. Okay, so that's the V1. And then rotate the hand like this. So we have our V1 this way, our V2 this way. In order to put your hand in that position, your thumb would be pointing straight into the page. And so our force direction is into the page with the magnitude that we calculated before. Okay, so you can write this as the force vector is equal to 2.403 times 10 to the minus 14 newtons directed into the page. Okay, well, by everything that we're used to, 2.4 times 10 to the minus 14 newtons is an absolutely tiny force that would have no effect on anything, except electrons are also, they have such tiny mass. We've never seen things like that before. And so what we're going to see is that there's a huge acceleration even from this tiny force. And so for part B now, so what's the acceleration? Well, we're just going to use Newton's second law. And we know that the force vector is equal to the mass of the object times its acceleration. And so we can calculate the acceleration as just equal to, we can think of it as the magnitude of the force divided by the mass of the electron. And it's still going to be in the same direction as the force. Remember, the acceleration and the total force are always in the same direction. And so the acceleration is 2.403 times 10 to the minus 14 divided by the mass of an electron, 9.11 times 10 to the minus 31. And that is 2.638 times 10 to the 16 meters per second squared. So even with that tiny force, we get an absolutely huge acceleration. Okay, well, this is the force and acceleration at a single instant. Now let's talk about what happens if there's a constant magnetic field and a single particle moves in a constant magnetic field. So we're going to talk about a charged particle that's moving perpendicular to a constant magnetic field over time. So the difference is the one we just did, we didn't do this calculation over time. We just said, this is what's going on at this single instant. Now we're going to say that at every point that magnetic field is the same thing, and what does the particle do as time goes by? Everything about this calculation is going to be pretty similar to the one before, but what's going to happen is the particle is going to move in uniform circular motion. And we're going to use the force calculation. So we're going to calculate that force vector, and we're going to use that to find the centripetal acceleration. Okay, so we're going to assume that that force is the only force acting on the particle, and so that force is going to be the only thing that provides centripetal acceleration. All right, so let's say in this case that our magnetic field is into the page. So we're looking at the feathers of the arrows. So this is our magnetic field. And let's say that at this instant, at the starting instant, our velocity vector of the particle is this way. Okay. So the magnetic field is perpendicular to the velocity. So we know that this is going to move in uniform circular motion. We're going to calculate our force using the equation for the force applied to a charged particle by a magnetic field vector. So we have the absolute value of the charge times the speed times the magnitude of the magnetic field vector. And we're going to set that equal to the mass times the centripetal acceleration. So mv squared over r. You can see right away that one of those v's cancels out. And this is the mass times the centripetal acceleration. Okay, so that's the approach we're going to use. And a common thing to use this for is to find the radius of the circular path, that kind of thing. So, okay. Let's say that we have an electron moving in a magnetic field where everything is coming out towards us. So this is the magnetic field. And the electron is moving this direction at an instant. And let's say that the strength of the magnetic field is 2.5 times 10 to the minus second Tesla. And let's say that I'll give the speed here is 8 times 10 to the 6th meters per second. And so first we're going to calculate the size of the circle, the radius of the circle. And then second, we're going to calculate the direction of this circular motion. We know that the circular motion has to be in the plane perpendicular to the magnetic field, but we don't know yet whether it's going to be, if you can see my cursor here, we don't know whether it's going to be up from this and be going counterclockwise, or whether it's going to be going down from this and be moving, because this magnetic field is everywhere, even if I didn't draw it below. You know, the magnetic field is still here. So this circular path also could be a circle where this is the top of the circle. So we want to figure out whether it's going clockwise or counterclockwise. Okay, well, the first thing we're going to do is just calculate that force magnitude and figure out the radius from the centripetal acceleration. The force is equal to the absolute value of the charge of an electron times the speed, which is 8 times 10 to the 6th, times the magnitude of the magnetic field, 2.5 times 10 to the minus second. And if you multiply that out, you get 3.204 times 10 to the minus 14th newtons. And now we'll set that equal to the mass times the centripetal acceleration. So 3.204 times 10 to the minus 14th is equal to the mass of an electron, 9.11 times 10 to the minus 31st, times the speed squared, so 8 times 10 to the 6th, and then that's squared, divided by the radius. If I was smart, I could have left the speed over here in the force calculation, and those two would have canceled out, but it's not a big deal. Let's just calculate it this way. So the radius then of the circle is equal to 0.00182 meters. So not very big, but about 2 millimeters, which means the diameter of this circle is 0.4 centimeters, you know, something visible to the naked eye. And if these electrons were given enough energy that they glowed, you could actually visibly see that circle, and that's a common experiment in certain physics classes. Okay, so that's the size of the circle. Now, which direction is it going to go? Well, all we have to do to figure this out is figure out at this point, when the electron is moving to the right, is the force up or down? Because we know that that force is toward the center of the circle. It's providing the centripetal acceleration. And so if that force is up, then this is a counterclockwise circle above that line. And if that force is down, then the center of the circle is below that vector that I drew, and it's moving clockwise in a circle like this. Okay, so our V1 for figuring out the force direction is the velocity, which is to the right, times the charge. So this is the velocity vector. But the charge is negative because it's an electron, which means that our charge times the velocity is this way. Our magnetic field vector is our V2 for using the right-hand rule, and that is out of the page. And so which way do you have to position your hand so that V1 is to the left and V2 is out of the page? Well, this is what your hand would look like pointing in the direction of V1. So this is your Q times V. If you curl your fingers out towards the out of the screen, this would be B, and that says that the force vector is up. Okay, so if for an electron that's moving to the right like this, if the force vector is up, and that's provides the centripetal acceleration, then the circle has to be above this vector because the center of the circle is above it. And that means that at the bottom it's moving to the right, which means that this circle is going this way. Whoops. It's all going the same direction. Okay, and that's all because we know that the center of the circle was above the point we were looking at, and this is the velocity at the bottom. Now, another application of the force on a charged particle applied by a magnetic field is the force that's applied to a current-carrying wire. Well, it really doesn't have to be a wire. It could be any conductive material, but usually you see it with wires. And the idea here is that all of the electrons in the metal of the wire, if there's a current going through this wire, then those electrons are in motion. And so because that wire is made up of current-carrying particles in motion, there has to be a force applied to the wire, just like there are forces applied to those individual particles. So an electric current comes from charges in motion. So we know that there has to be a force applied to a wire. So the magnetic field vector must apply a force to the wire. So let L be the length of the wire that's exposed to the magnetic field B. And we're going to define the vector L as having the magnitude that's equal to that length. And the direction is the direction of the current. Okay. Then the force on the wire is equal to the current times the length L times the magnitude of the magnetic field. And the direction comes from the right-hand rule, where V1 is the current times that L vector, and V2 is the magnetic field vector. So notice we're assuming that this magnetic field vector is constant over that whole length of wire L. Okay, let's do an example. So let's say that we have a wire that's vertical, and there's a current of 0.5 amp moving through the wire. And it's moving through a magnetic field that's directed into the page. And the length of wire that's exposed to this magnetic field is 0.3 meters. And the strength of the magnetic field is 2 times 10 to the minus third Tesla. And we want to calculate the force on the wire. The magnitude of the force, as always, is the easier part. You just need to know what the variables stand for. So the force is equal to the current times the length of the wire times the strength of the magnetic field. And so we get a force of 3 times 10 to the minus 4 newtons. And now we have to think about the direction. Okay, so the L vector has a magnitude of 0.3, and its direction is in the direction of the current. And so IL is, well, I don't know why I'm writing the numbers here, because all we need is the directions. We could calculate the magnitudes, but they don't really help us. So This is the direction of the length vector, which means that the current times the length vector is that direction. The magnetic field vector is into the page. And so our V1 is down. Our V2 is into the page. In order to position your hand, to use the right hand rule here, you'd have to have your fingers on the other side. Then when your fingers are straight, they're in the direction of V1. When you curl them, they're in the direction of V2. And that means that the force applied to the wire is to the right. And so now we have the whole thing. The force is equal to the magnitude and it's directed this way. That's a pretty small force, but in a case where you had more current or a stronger magnetic field or more length or whatever, you can pretty easily set up experiments where you can see the wire move as a result of that force. Okay, the last thing that we're going to talk about is the torque on a current carrying loop. So if you have a magnetic field, let's say it's going this way, and you have a loop of wire that's kind of flat in the plane of the magnetic field. And I'm drawing it as a rectangular loop, although this the same principle works for any shape of loop, but it's easier to make sense out of if it's rectangular. And you have a current that's going around the loop this way. And let's say that we'll call this height L for length, and we'll call this the width W. And let's think about the forces that are going to be applied to the four sides of this. Okay, well, one thing that I should have mentioned here is that in order for the magnetic field to apply a force to a current carrying wire, that current carrying wire, the current has to be perpendicular to the magnetic field. Okay, so that's a perpendicular sign. And you can see it when we did the example, the current is perpendicular to the magnetic field. Okay, so right away you can see that two of these four sides are not going to have any force acting on them. So there's no force on the top or the bottom because those are parallel to the magnetic field. Parallel to the magnetic field vector. Okay, so what about the one on the left and the one on the right? On the left, we have, well, we could calculate that force based on I and B and the length L. But let's just think about the directions. Figuring out the numbers is the easy part. So what about the directions? Okay, so I times L is down. The magnetic field is to the right. And so if this is our V1 and this is our V2, then to use the right-hand rule here, we have to have our hand like this, okay? Then we can put our fingers in the direction of V1, curl them to put them in the direction of V2, and that means that the force on the left wire is where a thumb is on the other side, and so that force is into the page. Okay. Now we'll go to the right side and calculate the force over there. On the right side, the current times the L vector is up. The magnetic field vector is still to the right. Okay, so in order to curl your fingers according to go from V1 to V2, you would have to have your hand in this position. The way the fingers are shown here, they're in the direction of V1. Then you curl them to put them in the direction of V2. That says that the force is going to be out of the page. And so this is the force. Then on the right side, the current times the L vector is up. The magnetic field vector is to the right. And so you need your hand facing the opposite direction. The force in this case is into the page. Okay, well, what happens to this loop if you apply a force on the left out of the page and a force on the right into the page? You can see that this will rotate. So if you, let's see if I can get this across. So if you have a force coming this way on that side and a force going this way on that side, the result of this is that this is going to rotate that way. And the amount that it's going to rotate that way is the moment that's equal to the force times the width of that. Okay.